On the check-in today, a couple of you asked me if I would do a couple problems from the homework set, chapters 10, 11, and 12, and here was one of them. Here's chapter 10, number 83. Chapter 10, number 83 goes with this diagram here, which shows a some sort of pulley with mass 500 grams. There's a mass 1 and a mass 2, 400, 600 grams, and they want to know what's the acceleration of the masses and what is the tension in each of the cords or strings. This one's pretty straightforward. We've done this one on multiple occasions, and what we're going to need is we're going to need a net torque statement for this. We're going to need a net force statement here and a net force statement here. Easiest way to do these is to draw some force diagrams. So let's do this first one. What we know here is that the Earth is pulling this guy down here with M1G. He's accelerating upward, therefore the tension T1 has to be greater than M1G. Here we go. A net force statement for him, F net on block 1, would be equal to the mass of 1 times the acceleration, which is equal to T1 minus M1G. Eventually we're going to have to solve for T, so I'll just do it here. T1 is equal to then M1G plus M1A. How about this other guy over here? If I draw the force diagram for him, we know the whole pulley is accelerating this way, so T2 has to be greater than T1. But this one's accelerating down, therefore M2G has to be bigger than T2. We want to write a net force statement for this guy. Net force on 2, M2A, which is equal to, in this case, M2G minus T2. Eventually I have to solve for T2. So T2 is equal to M2G plus M2A. What about the pulley? We look at the pulley. If we're going to draw a force diagram for the pulley, so here's the pulley itself. Now I know it's supported here. We have some vertical forces. I'm not actually interested in those. But I know there are 2 forces on the pulley. Here's a T1 and here's the T2. So the forces are balanced, but the torques aren't balanced. So let's do a net torque statement here. The net torque statement, well, we know it has radius R, RT2. Now, of course, there would be sine theta, but if I look at this R vector here, I can see it's perpendicular, so sine 90 is 1. So RT2 minus RT1. But what do we know about net torque? It's equal to I alpha. And in this case, because it tells us that it is a disk, I know that my moment of inertia for a disk is 1/2 big M R squared. And it asks us for linear acceleration, so I know that alpha is equal to linear acceleration A over R. If I put these two statements together, I'm going to do it up here. All right, I'm going to substitute both these in here and set it equal to this. So I have I alpha is equal to RT2 minus RT1. I is equal to 1/2 mR squared. Alpha is equal to A over R. This is equal to RT2 minus RT1. I have R squared and R, and I have an R up here. Those R's magically disappear. I'm left with, on the left side, 1/2 big M A is equal to T2 minus T1. This is why I saw for T1 and T2 earlier, because I kind of saw it coming. So if I plug each of these in here, T2 is M2G plus M2A. No, it's minus that. I said minus, but I didn't write it minus. Sorry about that. And then you have to subtract here this whole T1. So if I distribute this negative, I'm looking for A, so I'm going to get all my A's on one side. 1/2 plus, plus, and now we can just plug and chug. The big mass, it says it's 500 grams, so that's 0.5 A plus 0.6 A plus 0.4 A is equal to M2G, so this is 0.6 G minus 0.4 G. Now, if you use 9.8, you're going to get the textbook answer. If you don't use 9.8, you're going to get my answer. And when I calculated it, I combined these terms and divided, and I got A is equal to 1.6 meters per second per second. I think the book was like 1.57 or something like that, because they use the 9.8, which is no big deal. So now I have my acceleration, and if I want to find my tensions, I can do that pretty quickly now because I already have tension equations. So if I import this one over here, T1 is equal to, this actually is M1 times G plus A. Do you see that there? So I have M1, which is 0.4 times 10 plus 1.6. T1 is equal to 4.64 newtons. And then T2 it's M2 G minus A, 0.6, 10 minus 1.6, and T2, when I looked at it, was equal to 5.04. Again, the textbook answers are going to be slightly different because they're using 9.8 instead of 10, but that is my solution for Chapter 10, number 83.